Hello everyone. In this video, I am going to be making copper citrate. So how it's going to work is basically in my last video, I made copper carbonate and a little bit of copper hydroxide by reacting copper sulfate with sodium carbonate. Well, in this video, I am going to be reacting copper sulfate with potassium citrate. So to get potassium citrate, I'll first have to react potassium hydroxide with citric acid. So let me get the stuff ready. Alright, I had to prepare my chemicals. You see, my chemicals are stored in milk cartons, so I had to weigh them out. Here's my copper sulfate pentahydrate, citric acid monohydrate, potassium hydroxide anhydrous. So, right here is 84 grams of potassium hydroxide, and right here is 105 grams of citric acid monohydrate, and right here is 187 grams of copper sulfate pentahydrate. I'm gonna first dissolve these two in water because I need to react the potassium hydroxide with the citric acid. You know, as I was told that citric acid is extremely soluble in water, apparently you can dissolve around 1,500 grams of citric acid in 1 liter of water, which is crazy. Potassium hydroxide is also really soluble in water. The only thing I have to look out for is that potassium heats up when dissolved in water, but citric acid cools down. I can feel this on my face. It's such a cooling effect. If I have to guess, the temperature is probably around 22 degrees C. Oh, probably dropped. Now it's 19 degrees C. Well, I can't be too certain. But this is... Okay, no, I'm too scared to touch it on my face. Okay, no, not doing that. If I have to guess, maybe like 60, 70 degrees C. Potassium hydroxide heats up water. When it's dissolved, you can see that there's literally steam forming. But here you can literally see that there's a little bit of water molecules getting condensed on the sides because one cools down while the other one heats up. I'll let it dissolve for a few moments. Now, while I let my citric acid and my potassium hydroxide dissolve in water, I'll dissolve my copper sulfate. I heard that copper sulfate is not very soluble in water, so this might take a while. Oh, well, will you look at that? You know what's funny is that copper sulfate can make a lot of copper compounds. You can use it to make copper carbonate, copper oxide, copper citrate, copper acetate. So many copper compounds, which is very cool. The only downside is that it wastes a lot of money, so none of my chemical extractions, none of my reactions are making any money. In fact, this whole time I was wasting money doing my chemical reactions. But who cares about money here? I'm doing this for experience. Alright, now I let my chemicals dissolve. Give me another moment. Alright, so after around 30 minutes of stirring and stirring and stirring, this is how I stir in my conical flasks, by the way. I just shake it like this. I managed to dissolve all my potassium hydroxide, and it's not so hot anymore. And I managed to dissolve all my citric acid. You know, I have this kind of thing where I can eat lemon. You know, some people, they find lemon so sour that they have to dilute it like crazy. But I can actually eat lemons like they are apples. You see, I can cut up lemons, then I can just eat a lemon like normal without having to fear any sourness. Personally, I find lemons sour, but not that sour, so I can just eat them fine. The concentration of citric acid in a typical lemon is around 12%. However, this is around 40% concentration of citric acid. So, if I drink this, theoretically, I am drinking around 3 times, or to be exact, 3.333 recurring times the concentration of normal lemon juice. So you know concentrated lemon juice, you just squeeze a lemon, you don't dilute it at all, you drink it. This will be around 3 times the concentration. Let me give it a go. Okay, before any of you all say anything, I know my chemistry teacher advised against tasting my chemicals, so I'm doing this at my own risk. This is citric acid and it should be drinkable. Just don't demonstrate what I did. Oh god. Ah. Ah. Oh god. Okay. Yeah. That was sour. That was really sour. Okay. Okay. Holy. Okay, never mind. I'm not doing that again. Give me a moment. Alright, don't worry about me. I'm better now. I just chugged an insane amount of mineral water. Now I'm good. So this is citric acid and this is potassium hydroxide. If I mix it, I would create potassium citrate. The chemical equation is here. Let's start mixing. Oh my goodness. Do you see that? Okay, I don't know what is going on, but as I mix the citric acid with the potassium hydroxide, it should react to form potassium citrate, but for some reason it's causing the solution to boil. I don't know if I should be concerned about this. Okay, I'm very concerned. This kind of reminds me of the time when I was adding hydrogen peroxide to sulfuric acid, because you know hydrogen peroxide boils when you add it to sulfuric acid, which is why you have to add it slowly. This kind of gives me the same vibes. I don't like this. I did not expect that if I add citric acid to potassium hydroxide it will boil, but apparently it does. What is going on? Do you see what's happening? Oh my goodness, the solution feels like it's 90 degrees. I don't know what's going on, but apparently it's a violent reaction. And I'm very concerned. I don't like where this is going. Oh my goodness. If I add it too fast, will it go splody-wody? Will it explode? It also kind of reminds me of when I was adding urea to nitric acid. Oh my god. I don't like this. No, stop boiling. Stop boiling. Listen, solution. I am just adding citric acid to you. Potassium hydroxide, I'm just adding citric acid. And I'm doing this slowly. You're not supposed to boil. Jeez, it has a strange smell. It kind of smells like... I don't know what the smell is. It smells weird. I don't know if this is supposed to happen. This is... Okay. Give me a moment. Let me sort things out. I will add it slowly but off camera because I'm very concerned. Alright, I've managed to fully react it. I think I know what was going on. So, basically, when I was reacting the potassium hydroxide with the citric acid, it released a lot of heat to the point that the water will start boiling. Because you saw when I added the citric acid to the potassium hydroxide, the solution was boiling. So I suppose that I think this is a very exothermic reaction, which is why like the water molecules will start boiling. To prevent this from happening, basically to prevent like overheating and then an explosion of water vapor, what I did was I've put the solution in a refrigerator and I've let it cool for around 30 minutes. And then I took it back out. It was around like, it was a little bit cool, which was good. So then I added the rest of the citric acid and it was good to go. So right here I have my solution of potassium citrate. Once the copper sulfate fully dissolves in the water, then I will add the potassium citrate to the copper sulfate. When I react the potassium citrate to the copper sulfate, it should react to form potassium sulfate and copper citrate. The copper citrate will form a precipitate because it's not very soluble in water. But we'll see about that. So I'm still a little bit like a little bit traumatized by the sudden boiling, because it caused a little bit of burns on my hands. But that's okay. Alright, after heating for like around 30 minutes, I brought my copper sulfate solution to a boil and I managed to dissolve all the crystals. The reason I have to dissolve all the crystals is because I want to make sure the copper sulfate fully reacts. I don't want to waste any reactants. So right here, I'm going to mix my potassium citrate with my copper sulfate. When I do this, it would react to form potassium sulfate and copper citrate. The chemical equation is here. Let's get mixing. Well, good thing now is that when I mix, the solution doesn't suddenly boil. That's because it does not release that much heat. So I can mix this quite fast. From my perspective, the solution kind of changed to a little bit of a greenish color. You know, copper citrate is insoluble in water. However, there's no precipitate yet. That's because, although it's insoluble, it's not fully insoluble, so it's still slightly soluble. So what's going to happen is that the copper citrate is going to be a super saturated solution. I'm going to have to settle for like a couple days for the copper citrate to slowly settle as a precipitate. So I'm going to have to let this solution sit for like many days. I'll come back to it, okay? Alright, it's already been 1 week, and would you look at that, there's a little bit of copper citrate forming. The precipitate is building up. If you look really closely at the surface, you can see that a little bit of the aqueous copper citrate is turning into the solid copper citrate that is going to settle to the bottom as a precipitate. I'm gonna fast forward another week and give you guys updates. You know, I think you all saw this coming. I'm not a very patient person, so I'm not gonna wait for the copper citrate to fully precipitate out. So here's what I'm gonna do. Since there is still a lot of copper citrate that is in the solution form, I am not gonna throw it away. Instead, I'm gonna decant it into this conical flask, and I'm gonna let this sit outside, and I'm gonna let this wait for a few weeks. And I'm gonna get my first batch of copper citrate through the precipitate here. So I already waited a week. I'm not gonna wait another week. Okay. Now what I'm going to do is I'm going to filter this copper citrate through filter papers. I'm not going to show on the camera me filtering the copper citrate because I think y'all are already familiar by this point on how to filter mixtures. So I'm just going to filter out the copper citrate and get the residue. I'll deal with my second batch maybe like next week or something. I don't want to wait too long. It's been another week, and as you can see, there's some major improvements. So this is my first batch of copper citrate that I extracted, and this is going to be my second batch. Just now you saw that the solution had a dark greenish color. Well, now it's extremely light green. The greenish color has decreased significantly, and that's because a cyan precipitate formed. So I'm not gonna just filter it again like before, because that takes many hours. So instead what I'm going to do is I'm going to decant the potassium sulfate solution out. Then in case there's any stagnant potassium sulfate salt stuck inside, I'm just going to wash the residue with distilled water and decant multiple times until I get to the desired copper citrate. Okay, now that all that's over, it's been I think 2 weeks in total. I started this experiment at around October the 20th or something, and now is I think, okay, I don't know if it's exactly October the 20th when I started, but it's around the 20s in October when I started the reaction. Now is like the early Novembers, so it's been around 2 weeks that I was doing the reaction, because I had to wait a long time to let the copper citrate precipitate out. And turns out it was not the issue of waiting. I'll explain later in the video. But first of all, I'll just celebrate. Woohoo, I got my copper citrate. This is a beautiful blue-green powder. I am very proud that I managed to make this masterpiece. I tested its purity, it's around 95% pure. Beautiful. And another good thing is that, you know, I measured its mass in grams and the yield is 95%. 95% yield. I must feel like I'm a god of chemistry because 95% yield is insane. Typically the yield I normally get is in between 60 to 85%, but 95% yield. This is so beautiful. I can sell this online and make a profit. No, I'm not selling this online. It's too beautiful to be sold online. Anyways, one actual good use I can put on copper citrate is I can blast it in a furnace and it would decompose to form copper, metal, carbon dioxide, and water. But I don't have the heart to do that since this took me so much effort to make that I don't want to throw it away. I'm going to keep it in my cupboard as a collection and I'm going to worship it. It's so beautiful. If you wonder how many grams I extracted around 100 and something grams. 170 something grams, I forgot. Anyways, I think that's it. Before I end, I gotta explain something, so give me a moment. Anyways, before I end the video, I just like to say a few things. This is 215 grams. I don't know how I forgot earlier. But anyways, one of the mistakes I've made earlier was when I was mixing the chemicals, I added too much citric acid. So my citric acid was reacted in excess. This became a little bit of a problem because remember earlier when I reacted my potassium citrate and copper sulfate to form potassium sulfate and copper citrate? The copper citrate is supposed to precipitate out as a solid, but the reason why it remained dissolved was because there was still a lot of citric acid in the solution. And apparently copper citrate remains soluble in acidic solutions. I know this sounds very confusing. Personally, I was very confused at first. I did a little bit of research and yes, apparently in a citric acid solution you can dissolve copper citrate. To give you more examples, you know aluminium hydroxide is insoluble in water. However, it's soluble in a strong alkali solution such as sodium hydroxide. And then copper hydroxide is insoluble in water. However, it is soluble in a weak alkali solution such as ammonium hydroxide, also known as aqueous ammonia. And then zinc hydroxide is insoluble in water. However, it is soluble in both ammonia solution and sodium hydroxide. So, same goes with copper citrate. Copper citrate is insoluble in water, however it's soluble in citric acid. When I did a little bit of research and I figured out what was the problem, I got a syringe and then I filled it up with potassium hydroxide. Then I slowly added the potassium hydroxide to the copper citrate solution because I wanted to react the excess citric acid so that it does not remain stagnant in the solution, forming the copper citrate solution. The reason why I had to add the potassium hydroxide really slowly is because if I add it too fast and I add too much and overshoot it, then copper oxide precipitate would form. So I kept measuring its pH. So the pH at first was 2 to 3, which indicated the excess citric acid. So then I kept adding 2 milliliters for like around 20 minutes. I just kept adding until the pH was raised to around 6 to 7. That was when I knew that the pH was somewhat stable. Then I stopped adding the potassium hydroxide and I've let the solution sit for another week. And after that 1 week, pretty much all the copper citrate that remained dissolved precipitated out. Then I just decanted the solution and I washed the copper citrate. So when you guys are doing the experiment at home, don't add the citric acid in excess. Make sure don't add the citric acid in excess and don't add the potassium hydroxide in excess. You need to do mathematics. You need to be perfect at molar ratio, perfect at stoichiometry. If you figure out the exact ratio and the exact amount of grams, including all the decimal places, then you would be able to mix the citric acid and potassium hydroxide perfectly without any excess. But the only problem is that your chemicals may not be 100% pure. Well, it's the thought that counts. If you're unsure, then just buy some universal indicators online and measure the pH. If the pH is 2 to 3, then that means you added too much citric acid. If the pH is 13 to 14, that means you added too much potassium hydroxide. Yeah, I think that's about it. Anyways, I don't want to make the video too long because some people have bad attention span. Beautiful copper citrate. Anyways, I should probably go celebrate my beautiful creation. You guys can celebrate by pressing the like button and subscribing to me and following me on Discord. Thank you.